I upload a video to my YouTube channel, and in case if you miss something or maybe I speak too quickly or whatever reason, you can still wire to the tape, so it's going to be important. So last time we did was the momentum stuff, and then we'll talk about momentum conservation. And what's the definition of momentum? Do you guys still remember? What's the letter we use?
P.
P, and equals what?
NV.
M times V. Okay, good job, good job. You still remember that? Okay, cool. What's the condition for momentum to be conserved? What's the condition for momentum to be conserved? Anyone? Yeah. Yes, go ahead.
Isn't it when they collide, they stick together and end up both having the same velocity?
That's one type cases. Anybody else can add? Anybody else can add? Yes, go ahead.
Be elastic, right?
Be elastic. And can you add? Great. This is the excellent answer. Anybody else can add a little more? We need more students to add. What else we need to add?
Everything's in the same system.
Same system. That's good job. We're really, really wonderful. What else we need to add? Yes?
No net force.
Exactly. No net force on the system. I'm going to write down on the board. So that is a very important. Thank you, Dana. So in other words, when we say we have to distinguish two different things. One, the system, what the system is all about. That's very important. So the system, if the system includes two cards, net force, between them is called internal force. So you have to specify what kind of system you have. So what the system is. Second, which is most important, is your net force or external force, to be more precise. External force or net force, usually this will be considered as a condition equals 0. So this is the condition. There's no net force on the system. So I prefer to use the external force, because the net force sometimes does not highlight such a way that external force. When we say external, must be, could you guys write this down? External to the system. External to the system. Let me put the camera over here. In other words, what we have here is that the external, so-called external, what we really mean is that it should be the external to the system. So this is what it means here. Let me give you another example. Suppose I have a pendulum. So I have a string hanging from the ceiling, and watch carefully. If I have a string like this. Now this pendulum must swing back and forth, absolutely. Now momentum on this particular ball is not conserved. The reason was that, you see, let's look at horizontal direction. So here you have a tension. This tension is not 0. So in this case, momentum is not conserved. P is not conserved. Because our system is the ball. Because our system is a ball. On the other hand, if we include everything, now we're including the ceiling, the string, earth, everything, then the momentum is conserved. So it's kind of depends on which one you talk about your system. If you talk about this ball as your system, then this tension is going to be external force. Of course, gravity is also external force here as well. But the gravity is not on the horizontal directions. It doesn't matter. And so in this case, if you look at the horizontal lines. So this is the main reason. You see, it's very important to distinguish which one is your system and whether you have external force on it. So this is the good job. In other words, just to make sure this is the condition for the conservation of the momentum. All right. We will practice a lot. And if you notice the notes on this slide, something which is you must be very interested in. It must be have a similar problem will show up in the quiz. So therefore, you need to pay close attention in this particular example. So this example is about the train. And you can see the train before explosion between these two cars, between these two cars, explosion happens. So in the beginning, and so it's, we don't know which way this particular train moves. But after the explosion, we do know this car here moved to the left with 2 meters per second, while these 3 cars move forward like this. So that's what we have. Now you have A, B, C, D, E. You only have 4 cars. Just forget about E for the moment. Which one you would be correct? Could you show me your car, please? Okay, I saw these. And then, yeah, could you show me your cars? Especially those in the back. I cannot see your cars clearly. Yeah, raise your card. Okay, I see A, B, C, D. All of the answers would be possible. Do we have anybody D? Okay, well, D is possible. And we don't know which one is correct. We're going to figure out how. Good job. Let's see which one is correct. Okay, so here's analysis. Here analysis says the following. So in the beginning, whenever you see the positive, which would to the right, and negative to the left. So the final momentum, we know that. This is the final momentum. Let's look at the cards. So did you see the boss just simply use these ones? It should be kilograms. I think you misspelled like this. Meters like this. Yeah. 3 cars. And folks, I will correct this. This M is not correct. Units should be I'm going to write that down on board. This M. Oh, probably he meant mass. All right, that's fine. So that little lowercase m means the mass of the car. Could you guys write down in your notebook? Because there are too many m's here. Did you see we have meters here? This m is a mass. I wish we write them down. Folks, let's correct them to the capital letter. Folks, in your notes, could you write on the capital letter instead of the lowercase? Just get confused. Okay, so this is we're calculating the final momentum. And the final momentum, what we're doing is that, you see, we have one car move to the left. So therefore, it gave me a negative velocity. And so that's the velocity. And then the mass is 1 capital letter M. So this is that amount. And we have 3 cars. You see, that's 3 capital letter M here will be 1, 2, 3 cars. And the velocity 1 meter per second. You see, this value is a positive. This value is positive. So therefore, the initial momentum must be positive. So in other words, and you're going to see the next ones, you will see, so the correct answer should be to the right, is a positive. So the correct answer. So for those of you who got it wrong, please let me know whether you still have questions on this. Okay, so so it must be to the right because the initial final momentum must be conserved. All right. So now this time we have another question. And a cart collides elastically with a blow cart. Which of these following final velocities are possible? Could you guys spend about 3 minutes to work on this, and I will come back to this question. Okay? Yeah, you can take a screenshot, and so we'll come back. Which one is correct? All right. We're going to walk around. If you have questions, please do let me know. 5 minutes starts now. Okay, so we're going to check you guys at let me give you 5 minutes, should be enough, I think. If you got an answer, please check with your neighbors, see whether your neighbors and yours agree with each other. Check with your neighbors, see whether you got the same result, all right? Check with your neighbors, talk to your neighbors, see whether you get the same result or not. Remember, colliding elastic, what that means? Elastic. Elastic, what that means? Talk to your neighbors, see what your answer is. Anyone figure it out? Anyone figure it out? Which one is your Did you check with your child? Check with your child. Which one do you think? You think? Okay, did you talk to everyone? Talk to talk. Please talk to each other. This is your class. Oh, please talk to each other. All right, please talk to each other. That means that you are right Which one you decided on? You B. So I heard of A, B, C. So 3 of them. All right, which one we don't know yet?
The momentum.
Okay. Yeah. So if you look at the momentum itself, all of these are actually good, right? If you look at the momentum, all these are good because you see, if you look at the momentum, initially this will be the essentially 3 kg/meter per second, and this is 0. So everything adds up. This one will be good, and then finally, and if you look at this ones here, it's also 3 the same. So you know, if you look at the momentum, all of them are actually correct. All of them, A, B, C, all correct. But they say, well, I'm very happy. All of them correct answer. But then there's one thing hiding. I hope that the boss showed this reason. Did you notice there's a word called elastically? Did you see elastic? What that means? Anyone can tell what that means? Elastically.
Conserve.
Is it conserve what? Conserve what? Exactly, conserve mechanical energy. In other words, on the level, which means the moment of the kinetic energy has to be conserved. So I'm going to write on the board. This is so important. When you see the word, it says elastic. When you see the word elastic, this will be tells you the mechanical energy will be conserved. You know, the final initial must be exactly the same. There's no difference. Now, on the same level, there's no potential energy change in our case. In our special case, because the potential energy is nothing affected, so therefore, the kinetic energy is going to be conserved. And this one has consequence. Let me show you the bottom here. So in other words, the correct answer should be B. And you say, ooh, if I get A, what went wrong? Well, let's see why it is the case. Now, again, the momentum are all exactly the same. So there's no difference. You see, 3 kg/meter per second, every one of them are good. But if you calculate the kinetic energy, you see the initial kinetic energy is 4.5 joules. You can apply the equation, only first mass has the velocity, that's why you get this one here. But in A, B, C, they have different kinetic energy. Did you see that? Can I get a thumb up? Everyone see that? Yeah. So this is the main reason. In other words, all of this have different kinetic energy now. The one that matches my initial kinetic energy is the plot B. That makes sense? So that's the main reason why B is correct. Anyone has a question? So this is just to remind you, when you see the elastic collision, just be cautious. Just be cautious, because elastic collision means that the mechanical energy is conserved. And that's the key word you need to remember. Now let's do this one. This is another one. You're going to read that. Which one is correct? Yeah. Again, 5 minutes. Reading. You got an answer. Show me your key, please. Which one is correct? Yeah, if you got it, you saw some show me C. C is the same speed. Okay. All right. Give me 2 more minutes. Think about it. You got C. Good. Anyone got A there? Where is B? Where is C? What is yours? What is yours? Which one is correct? I'll make a guess. All right. Which one is yours? Talk to your neighbors. Talk to your neighbors. Talk to them. Which one is correct? Who's going to agree on that? Yeah, talk to your neighbors. Talk with your neighbors, all right? Talk with your neighbors. Talk to your neighbors. Which one is correct? So I'm going to see. All right. Okay. All right. Now, show me your card. Find the answer. Show me your card, please. C. Okay. All right. Thank you. So we don't know which one is correct. Let's see which one is actually correct. So this time, and we have a little bit explanation of what's going on. The first part is that total momentum start at 0. You know, there is 0 momentum to start with, so the final momentum has to be 0. Now, this time with something which is very crucial. In the end, Billy, she's going to holding a bowling ball. So her mass effectively will be larger than Ashley's, right? Because they both have the same mass, but when you hold a bowling ball, of course, your mass will be heavy. Makes sense? Your mass will be heavy. But momentum and both of them will be the same. And the Ashley and the Billy, they have same momentum, but the Billy has a ball with her, so her mass is larger. So what happens to her velocity was? Yeah, velocity will be smaller. So in other words, I'm going to show you on the board what happens. Okay, let me write this down on board. Folks, I'm going to erase, can I erase this part? I'm going to erase this part. Okay. So I'm going to show you now. So momentum actually, I use letter P sub A to represent it. That's a momentum actually. And momentum of Billy I use the letter B to representing that. Of course, the directions are opposite, so they differ by a sign like this. So that's what they have. The amount will be exactly the same, but direction is just opposite. But now, actually, her mass is just M, A, B, A. That's her velocity. The Billy equals a negative. Now watch carefully. Her mass is the same as her sister, so that's the exact same ma. But she has to add one more thing. There's a ball added. Did you see it? She has a ball there, and then a BB. Now you see the mass smaller here, larger here. So therefore the BB will be what? Bigger or smaller? Smaller. And this will be smaller. That's why the person carries the ball is going to have a smaller velocity, and that's how it happens. And so this is you see, Ashley is going to move faster. So her sister is going to move faster, and the Billy will move slower. So that's conceptual understanding. Do you want to practice on this? Show you the real number? Let's show you the real number, shall we? Okay, let's show you the real number. This is just conceptual understanding. And, okay, let me show you the real number so that way you have a better understanding what is happening. This time, folks, we're going to use the real number now. So this is a real number calculation. So which I'm going to do right now. Put the camera over here. So we're going to put some numbers. We invented some numbers here. So let's put the mass equals maybe 70 kilograms. How about that? 70 kilograms. And the both of them the same, of course. Let's put the actual velocity, let's say 5 meters per second. Actual velocity 5 meters per second. And we're going to put the ball here. The bowling ball, what's the weight usually you have? You guys remember? How many? 8 kilograms?
No.
Oh, you do some pounds.
14 pounds.
14 pounds. How many kilograms? I need a kilogram. 7 kilograms. Oh, that's no, it's impossible. I can just use a smash too. Let's put the number. How about 3 kilograms? I think 3 probably is reasonable. You remember one day? About this, right? Okay. Let's do the 3 kilograms. All right. So this is the number which we have. Folks, I want you to find a VB. How large VB is going to be? Yeah. 2 minutes calculation. I want everybody to do the calculation, not just 1 or 2 students. If you still have questions, please do let me know. Measure your calculation, and when you get it, check with your neighbors. That way, the neighbor will be very happy. Check with the neighbors, see how large you guys got. So not only do we understand the conception as well as the numerical. Check with your neighbors, see how large you got it. If you have difficulty to solve this problem, could you show your hand so I will come over to help you? Where's your equation? Let me look at that for you.
Yeah, negative 4.7.
You're looking for BB. Okay, so you're looking for BB on the left hand side, on the right hand side. Yeah, and yeah. So now we'll just write a BB here. Now we have equation. To solve this, how do we solve it? Yeah, so what you do, you calculate how large this guy is first. Yeah, just write it down. Just do the calculation. Yeah, just 7.3 times the Any help needed? Any help needed? Yes, section 73. Yeah, 73. Parenthesis. Put parenthesis there. Yeah. Parenthesis and BB. Yeah. BB. That's B sub B. Yeah. So you have 73 BB equals 73 BB. Exactly. And then solve for. And then the left hand side you have 70. Just put a 70 there. 70 times BA, which is 5. Times, not divided by time, multiply by. Yeah, multiply by.
Yeah.
Times, exactly 5 equals 73. You got it? BB. And then you can solve for BB. Divide by 70. Yeah, did you get it?
Negative 4.7.
4.7. You got the same result? What about here? Did we get the same result? If it's the same result? No? Okay, all right. We will go over this. Anybody else have questions? Anyone figure it out? Figure it out.
Because I have so many scholarships and they refund. Yeah, I have like 13 grand.
Dude, that all
How about here? Should we get the result?
Yeah, they send me I see about zero.
All right, folks, we're going to convene now. We're going to do the calculation. And we're going to show you how do we do that step-by-step fashion. Okay, so this is how do we solve it. Did you guys see we have this equation? Did you see my MA equals 70? So I'm going to write it down, 70. My VA equals 5 meters per second, so I'm just writing a 5. So that's what we have left-hand side. And then equals a negative. Now this is 70 plus in ball, which is 3, times the BB. From here to there, if this, you understand it, could you show me your card A, please? From here to there, show me your card A, please. Or just sum up that one. Okay, very good. Card A, card A. Okay, very good. Now, we're going to add this up. 70 plus 3, of course, 73. That should be straight enough. And 70 times 5. How large? 70 times 5? 350. 350. Good job. And what we do next is that both sides divide by 350? No, we divide by what? Negative 73. Negative 73. All right. For those of you, yeah, question.
why would the 73 be negative?
Because the initially, it's a negative there. And well, that's actually a great question. Essentially, what we're saying here is the initial final momentum is always adds up equals 0. That's why if you move this guy to the right hand side, you get a negative sign. That is a negative sign comes out. So now we got a VB. These two cancels out. So how large you guys got? Yeah. 4 point what? 4.79. And can I get one more stick please?
5.
5. Okay, that's wonderful. And it should be meter per second. So how many of us got the same number that I showed on board? Could you show your hand, please? Let me enjoy it. Oh, that's my result. Sweetie. Good job. You guys did a good job. So you see this number, absolute value, is really smaller than this one here. You see that? That's what conceptually makes sense. All right. So this is what we get here. Now, any questions on this? Any question on this? That's how do we do the calculation to convince ourselves. Now, I want to show you one more concept. This concept is a very useful concept. It somehow relates to the momentum, which is called impulse. Now, the impulse is a new concept to us, please. And I want to show you why this comes out. Why we need this, the force comes out. Now, you saw Dr. Bartz has equation like this, which is a really wonderful. But the impulse defined as something which is very weird. Did you see the impulse defined as the momentum change? Not the momentum change. And I want to show you why we got this equation comes out like this. So we're going to start with the, you remember force just equals mass time acceleration. And acceleration is just the delta V over delta T. We mentioned last time when we introduced the momentum. So then m times b is interpreted as the momentum delta P over delta T. So in other words, that we end up with this equation. So when we introduce the momentum, and we said this is the equation m multiplied by b, and give me p. That's the momentum which we have. Now, what you're going to see me, I'm going to do both sides and multiply by delta t. Delta t. Now, when you multiply delta t here, this is delta t, the numerator is going to cancel out, so I get a delta p, like this. So now, this particular expression, force times delta t, is defined as the impulse. So that's why you can see here, I have I equals delta p. And these two equations are actually come from the same idea. There's nothing different. Essentially still from this equation, and it gave me this particular result. So that is the so-called impulse equals force times the delta t, or just the momentum change. These two are completely equivalent. And if you look at the map, if you look at it graphically, the impulse is just this particular area that you're going to see, and that's called impulse. The area itself is the impulse. So the integration area is called impulse. Now we can approximate them into average ones, and then we get this particular results. So that's called I equals F average delta t. These are all beautiful mathematics. These are mathematics. These are mass definition. And now I'm going to show you physics, what the physics is. This is a mathematical definition. Why we need to introduce impulse. So I want to show you what the physics here is going to be. So bottom down here, and I'm going to show you the physics. On the top, you can do the mathematical manipulation, same results, that's always the same. Now where the physics comes out in this part. We're going to use this equation as an example, just this part of the equation as an example. So we have I equals F times delta t. Both sides divided by delta t. So my delta t on the right hand side is gone. And this equation shows you the physics. What do I mean by showing the physics? Did you guys remember when you were young, you jump from the table to the floor? Do you bend your knees? Do you bend your knees? Do you? You always bend your knees. Why bend your knees? You absorb some contraction, yeah, you will say that. What actual physics does is you make delta t larger. It's made larger. You make your delta t larger. When the delta t larger, the force is smaller. That's usually sometimes you can cushion something like the same idea. When you sit in your car, you always have a cushion sitter. You never sit like this, right? You ever tell me I'm gonna sit on this? I'm gonna drive every day. Then you will drive like a truck. So a truck like this, it's going to be not very comfortable. And you know these tanks, those tanks, you know inside a tank, you never been inside that probably. The tank usually people are standing there because you cannot sit there because it's just bumping so much you can't do it like that. Why? They do not have this larger delta T. Okay, so the larger delta T. And every cushion we use is always used like this. Another thing which we use in the cars, you remember the cars driving, and there's always the airbag in the driving wheel. This airbag, boom, pump out. You probably never see like this big, huge. Why are they doing this? Make this delta T larger. That's physics. That is physics. And similarly, if you punch something really, really hard quickly, you're going to make this delta T larger, so the force will be larger. You remember when you have a hammer hit on this, it goes like this, right? The reason was that the delta T is smaller, that would be larger. In the football, you guys remember they wear these special shoes on the top, it's very thick one. Why are they doing this? Make delta T larger. Exact same thing. So this is a key idea. You see, this is the mathematics, that's the physics. The reason why we insist right in this format, not above format, is that above format creates the impression to you that, okay, my impulse equals force times delta T. No, that's the mathematics. True physics is down here. This tells you if you make T larger or smaller, will affect your force. Even with the impulse hold constant. That's when you introduce a new idea called impulse. Let me show you a little more slides, and you will see why we need this. All right. So I'm going to show you one more slide. This is actually my zero. And this one is quite interesting. Tell me which one is the best to throw at the door to close it. Don't close. Which one is it closing? A, B, or C? Some of it is A, some of it is B, some of it is C. All right. Okay. Now, the first one is a clay. Remember, Lambo clay. It is going to stick on the door. Boom! Stick on the door. Watch out the second one. Beanbag. And beanbag slightly bouncy back, but not a whole lot. And the last one is a bouncy ball. It's going to boom, bouncing back. So now you see I threw the same thing into it. If you look at that, in the beginning, before the collision, and assuming they are exactly the same, so you see, they all equals a P1. Everywhere is a P1. Exactly the same. But now watch carefully what happens after the collision. After collision is a P2. We don't know how large that is. But second one is definitely 0 because hit on this, boom. The last one is a negative P1. Now, remember this is the momentum. Now we have the momentum change. So this is how much momentum changed on the door. So that's a delta P. Remember that's the physics side of delta P. That's delta P. This is a P1 minus P2. Second one is a P1. The last one is a P2 P1. You will see definitely this one will be larger than this one because the momentum change is larger. In other words, did you see momentum change larger? This I will be larger, the force will be larger. So that is what happens. And now you can see the results here. So the number one would be this one here, and second one, this one, third one. I don't know how Dr. Bond's created these kind of things, but I want to show up. This is not my creation, that's what they do. Okay. You guys got it? Got it? So that's the key idea. Alright, so once we got this key idea, now we're going to move on to one of the very important topic today. We probably won't have enough time to finish it but I think this is a good idea to let's get started together. Folks, I'm going to show you the, I prefer to use the simpler ones that instead of the harder ones. Okay, so here is what we want. And I'm going to write down what we will ask to do. So this is the, I'm going to call it example 1. So the calculation example, I call example 1. First, could you guys write this down? Oh, I ran out of ink. I need to put another one. Is this better? Oh, yes, this is a whole lot better. First, could you write this down? This is number 1 example. And this example is so-called a perfect inelastic collision. So in other words, our first example is called perfect inelastic collision. And we have, so essentially, suppose we have 2 cars. The first car is over here. Did I draw my car very well? I think I did. But by the way, this is the only one that I can draw very well. And this car, M1 equals 0.7. It's just toy cars. Its mass is this amount. But it has a initial velocity v1, vi. So initial velocity, do you see I have optical ones? I use v1i. So that's my initial velocity. And I believe this is a 0. So that's a 0. And the second car, we know the mass. So there's another car, M2. Let me look at the mass. Oh, he did not use the same mass. Let me put in same mass, exact same. Same mass. But this car initially moves V2i. You see I use car 2, just V2i equals 3 meters per second. So that is initial condition. So this is the one which we have. And I'm going to write an initial. You know, initially this car, forgive me, this will never colliding. If this guy stands still, this never, could you guys change this to 3 meters per second? Forgive me. If this guy doesn't move forward, there's no car behind. I didn't realize there's a problem. Folks, forgive me. Okay, so otherwise they won't be able to colliding at all. So this car moves forward. All right, that's initial condition. Finally, which I'm going to write over here, they're going to stick together. So this is the final. Finally, these 2 cars are stuck together. Maybe one car is wrecked completely. And then they stick together. So therefore, their final velocity, v1f equals v2f. So the final velocity must be the same. Now, this is due to the fact we have a perfect inelastic collision. So these 2 is directly consequence why we get same velocity. So the question is that find v1f or v2f. Okay, let's do that. So we know the initial condition, and that's finally, and let's do that. I want you to do it within the 5 minutes. Yes, about 5 minutes. That's good time. So this is the momentum conserved, and we wanted to try to find out how large that is. So the initial and the final momentum are exactly the same, and you're going to calculate how large that is. If you do get lost, raise your hand. I will come over. Make sure the next. up. Maybe let me take a look at what we got. Exactly. Can they stick together? Anyone else finish? If you want me to check it, I can do that. Yeah, I'll do it. If you want me to check it, yes, sure. Yeah, make sure to raise your hand if you want me to check it for your calculation. This means reading here.
That's a great question.
It must be smaller, right? It must be smaller. It must be smaller than 3 meters, right? It doesn't matter because this comes in the molar conjugation. We're not talking about the force. We're talking about the forces, then we do the all right, let me show you. Folks, I'm going to quickly show you how we do the calculation. We may run out of time, but I'm going to quickly show you. Did you see my initial, this is my initial condition, so I'm going to calculate initial momentum, which means going to calculate. So my P1I plus P2I, I want to calculate initial momentum. To calculate this, it's just this number, mass times velocity, 0.7 times 3. Because my second mass has 0 velocity, the momentum is 0, so I don't need to do anything with that. So this gave me 2.1, like that. That's initial momentum. My final momentum, P final, because these two stick together, so therefore M1 V1F, M2 V2F, M1F, M2F are exactly the same, so I can pull these guys out. V1F. Now these two masses, exact same mass, so 0.7 times 0.7 up plus 0.7, I got 1.4, and that's a V1F. This whole calculation equals 2.1. So that is why we get calculation. Folks, could you do me a favor? Calculate V1F divided by 2.1 divided by 1.5. 1.4. 1.5. Okay. V1F equals 1.5 meter per second. So that's how to do the calculation. I realize we're out of time, and Wednesday we will show you a little more detail. So that's it. See you guys on Wednesday. Wednesday we have a quiz. Make sure do not miss that. So I'm going to stop the recording.